Good morning. Today we are going to talk about the mole, and you're going to be learning some more about how useful the periodic table is going to be to us as a tool as we head into the concept and really just begin the concept of stoichiometry, which looks at the mathematical side of a chemical reaction. So we're going to begin by defining the term mole. And we actually talked about moles much earlier in the school year. If you remember way back to a lab where you added drops of water to a penny, and then you figured out how many molecules of water were held on there, or you figured out how many atoms of carbon were in your signature, that was all tied to the mole. It's just that you really didn't have a grasp on what a mole was at that time. So that's what we're talking about today. A mole is the SI unit for amount of a substance. And just like a dozen is a unit that, say, Dunkin' Donuts would use, or a baker's dozen, which would be 13. A mole is a unit that chemists use. And the mole, or the concept of the mole, which is abbreviated MOL, allows chemists to count particles by massing them. So, 1 mole, and you can pause this recording at any time when you need to catch up on the notes. The notes are also available on the Chem 1 website in the mole unit, and today's topic is molar mass. Okay, well, a mole of any substance, doesn't matter what it is equal to 6.022 times 10 to the 23rd. And we call that Avogadro's number. And it's the number of particles that are in 12 grams of carbon-12. It's kind of like the baseline for a mole. But for our purposes, how we're going to use it in Chem 1 is we're going to use this Avogadro's number to help us convert between particles, which could be molecules, formula units, atoms, and then the mass of a substance, so that we can really dig more deeply into the quantities involved in a chemical reaction. Well, this 6.022 times 10 to the 23rd is obviously a large number. You can tell that from the exponent. But if you remember way back earlier in the year when we talked about numbers in scientific notation, how you can lose the grandeur of numbers. Well, just to give you a frame of reference to help you better understand how large a mole really is, let's put it in terms, say, like money. If I had a mole of pennies and spread them out evenly throughout the world, so there's 7 billion people in the world, each person would be able to spend $1.6 million per minute for an entire year. That's how big a mole is. It looks deceivingly small when you see it as 6.022 times 10 to the 23rd, but it's a very, very large number. Well, let's see how to use these values now as we move forward. Well, 1 mole of copper equals 6.022 times 10 to the 23rd atoms. Because copper is an element, and the smallest part of an element is an atom. Now, just to kind of review that concept of bonding, remember copper was a metal, and in a metal you've got those cation cores, and then you've got those electrons that move freely, flow freely through that metal, which give it the properties of malleability and ductility and make it easy for it to conduct heat and electricity. Well, if we move beyond thinking about individual elements and we start to think about compounds and look at something like water, which is a covalent compound, And covalent compounds are formed by the sharing of electrons. And you remember what water looks like. We've seen it a number of times now with that bent shape. And then we've got the dipoles. So we've got the slightly negative and slightly positive end of our polar water molecule. But that's the smallest. This H2O is the smallest unit of water that keeps the properties of water. Well, a mole of water, notice the similarity, is 6.022 times 10 to the 23rd molecules in a mole of a covalent compound. Well, there were some other compounds we learned about, and we put these together, these chemical formulas together, doing T-charts. Say, for example, calcium chloride. Well, chloride is the anion, and chloride has a -1 charge. Calcium has that +2 charge. So it takes 2 of the chlorides to balance the 1 calcium. And so if we have a mole of the ionic compound calcium chloride, goes together CaCl2, and if you could zoom in and see that at the atomic level, you'd see that recurring lattice, that repeating pattern of the positive, negative ions held together as that crystal. Well, even though it's substantially different in its properties than water or elemental copper, notice the similarity in that if you had a mole of calcium chloride, you'd still have 6.022 times 10 to the 23rd, but the smallest part of an ionic compound is called a formula unit. And a formula unit for calcium chloride would be 1 calcium and 2 chlorides. But the key again is that when you have a mole of something, what you have is 6.022 times 10 to the 23rd. Well, now that we better understand what a mole is, and again, it's just a really, really, really big dozen, we can see how we're going to be able to use the mole to mass substances. So the next part of the notes are going to talk about molar mass. And what molar mass is, it's the mass in grams for 1 mole of a substance. And we determine molar mass really quite simply. So I'm going to go through and just give you some molar masses and see if you can see the pattern in the molar masses. And I would ask that you pause the recording after each one of these examples so that you have a chance to think about the pattern before I actually explain the pattern. So if you have 1 mole of copper, not only do we know it's 6.022 times 10 to the 23rd atoms of copper, but we know that that equals 63.55 grams for copper. Now, we saw that this value is a mole of anything, but this value is unique to copper. Pause the recording and see if you can think why or figure out why that is the mass of 1 mole of copper. Okay. Well, you'll be able to check to see if you're on the right track if you can answer this one. We know that 1 mole of carbon is 6.022 times 10 to the 23rd atoms. But are you able to figure out that if you put it on a balance, that it would be equal to 12.01 grams? Because that's the molar mass of carbon. There are 12.01 grams of carbon in 1 mole of carbon. I'm going to have you pause it one more time, see if you can figure out where that value came from. And for the next one, I'm going to show you how to get the numbers. Okay. If you have a mole of iron, well, again, no surprise here. You've got 6.022 times 10 to the 23rd atoms. But if you take a look at the periodic table and you see the average